very exciting, right? Like, whoa! All right. Are there learning objectives on this page that you would like clarification on, or you want more information about, or anything? If not, we can move on to other things. It's totally fine. I just throw that open. Or on the second page, we can talk about the second page also. Maybe if I can get it to go. There were 2 pages on this one, right? Or no?
Yeah, there were.
Oh, my computer's being so goofy. It's just like tired or something. There it goes. On the other side, is there anything on the energy pages that you want to go through or talk about?
Yeah. What about the 5B 2.1?
Was that on the same page, on the first page or the second page?
Second page.
5B 2.1, the very last one?
Yeah.
All right, let's take a look at that one. It says, the student is able to calculate the expected behavior of a system using the object model to analyze the situation. Then, when the model fails, the student can justify using conservation of energy principles to calculate the change in internal energy due to changes in internal structure because the object is actually a system. Okay, so what does that mean to you? Because that's a lot of words, right?
Yeah.
Yeah. Ideas, thoughts? What does that mean?
You have some object movement doing something, and then you calculate its energy, and at the end of its traveling or whatever, it isn't where you think it's supposed to be. You can say that something happened internally to its energy.
Okay.
You know, like a rocket.
Okay.
Or a kid on what are those red things that you pull stuff in? Wagon. There we go.
I was trying to follow your brain there. Yes. Yeah. Okay. Or frogs. For example, what kind of energy do you have right now?
Gravitational potential.
Gravitational potential. As he falls, what happens to that gravitational potential? Goes down, right? And what happens to it?
Changes to kinetic.
Changes to kinetic, right? But then when he gets to the bottom, now what? Does he have gravitational potential? No, if we said H equals 0 at the floor, right? Does he have kinetic? No. So it appears that he had a bunch of energy, right? And then it converted to kinetic, and we still conserved energy, but now there's no energy. Does that make sense? Where is the energy?
Dissipated into the floor.
Dissipated into the floor, but not only that, what else happened to him? Sound. So sound dissipation, and what else internally? What happens when you rub things together a whole bunch?
Heat.
Yeah, there's some heat. So that's what they're talking about here, is that there is a change to internal energy. You remember I had that big tube out with those ball bearings in it, and I made the big loud noise, and I told you that there's a lab that we do and we'll do next year that has like little ball bearings, and you actually measure the change in temperature, right? It doesn't seem like there should be a change in temperature because it's not like you're putting it by a flame or something, but that's what's happening. The internal energy is shifting. Does that make sense? What else from the yellow one, from the energy page, can I help to clarify for you? Anything else from that one? Everything else seemed pretty straightforward?
I just have like a question. I don't think it wasn't like covered in here, but I was just like thinking about it. Can you go over like the impulse?
So impulse goes with momentum.
Yeah.
We can.
So that would be later.
Yeah, that'll be in the next one, probably.
Oh,
Yeah.
okay.
But yes, we can certainly go over it. Yeah. More stuff on this one before we move on? Okay. Well, let's go on to that. So momentum, this one was maybe some sort of light other color. I don't know.
Yeah.
What do you want to talk about from this one?
Impulse.
Other people? Anything else? Like, are there learning objectives? We'll talk about that in just a second. Donald, I'm not trying to put you off. I just want to make sure that I don't miss any other opportunities here. Other things? Are there any learning objectives that are like, what is that?
Those are 5D14.
5D14, sure, if I can find it. I hate this. I wish it was like, so, okay, 5D14, I found it. Yes. So I'm looking at 5D14. It's on the back of my page, halfway down the first column. It says, a student is able to design an experimental test of an application of the principle of conservation of linear momentum, predict an outcome of the experiment using the principle, Analyze data generated by that experiment whose uncertainties are expressed numerically and evaluate the match between the prediction and the outcome. So basically that means, can you do a conservation of momentum lab?
Why couldn't they have just said that?
What's that?
So why couldn't they have just said that?
Because they like to use, maybe they get paid by the word, I'm not sure. So that's basically what it's saying. It's a lot of words, right? It's kind of ridiculous. But basically it's saying, if I got out a cart and a track and two carts, and we collided them, and we videoed it, and we measured masses, and we measured velocities. If we might have, perhaps, potentially, you could make a prediction before you did it about what was supposed to happen, and then you could make measurements, and then you could compare your measurements with, that's what it's saying. Yeah. Just in a ridiculous number of words.
Yeah.
Just to intimidate small children, I think. Yeah, and it was successful. What else? Is there anything else from this set that you want to talk about? Yeah.
3D11.
3D11. Is that on the same side or a different side?
I think it's at the bottom.
3D11. There it is on the back, on the other side, on the very bottom. The student is able to justify the selection of data needed to determine the relationship between the direction of a force acting on an object and the change in momentum caused by that force. The student is able to justify the selection of data needed. So, in order to measure a force, right, you either have to have some sort of force meter, right, or you could measure mass and acceleration. So I think that what they're trying to say there is that you can identify what data you would need to collect to find the force.
Okay.
That's how I would read that. And to determine the relationship between the force and the momentum. So this is what Donald wanted to talk about now. See, I told you it was going to work out for you.
Yeah.
Thank you to Michael for, making it work out. So if we talk about this, let's talk about impulse. What is impulse?
Change in momentum.
It is. It's change in momentum, yeah. And change in momentum is equal to force times. Do you remember?
1 over c.
It's not force times 1 over time. So it's actually momentum divided by time is force, which is Newton's second law, right?
Okay.
Yeah, so F times T. So the deal here is, and this is how it fits in here, determine the relationship between the direction of the force and the direction of the change in momentum. Is everybody okay with this statement? Yeah.
Is force average force?
Net force. So it would be, that's assuming a constant force.
Okay.
If it's not a constant force, then you have to use calculus. Yay! But we don't have to do that. Yeah. So this comes from, just a nice little reminder here, you know that F net equals MA, yes?
Mm-hmm.
Yes. So A is equal to change in V over T, right?
Mm-hmm.
And M change in V is really just change in P over T. Is that okay?
Mm-hmm.
M delta V is equal to delta P.
Mm-hmm.
So then I just left the T there, and then I'm going to move that over, and that's where this comes from. Yeah, so these are really equivalent statements. They're the same thing. Okay? So the second little piece of that learning objective 3D11 says a relationship between the direction of the force and the direction of the change in momentum. So if a force is acting to the right, that means that the change in momentum is also going to be to the
Right.
because it's the only two vectors. Excuse me. Does that make sense? Okay. So if it's speeding up, it's going to speed up to the right. If it's slowing it down, right? Correct. Does that make sense? So if it's moving to the left and the force is this way, it's going to slow it down. That's what this is saying. That's what that piece is saying. Is that okay? What else do you want to know about the impulse momentum theorem?
I was just wondering, like, if there's something that was saying, like, if a ball with a certain velocity or something, like, hit a wall,
Okay.
and like rebounded off, what would the impulse be?
Be the change in momentum.
Be the change of momentum.
Yeah. Impulse. Impulse is a funny thing because there's not like a letter that goes with it, right? It's not like I, because I is for current, right? So we can't use that.
Yeah.
Impulse is just change in momentum. That's all it is.
So you just find like the F net and the time. And
Or you'd find the change in momentum. Don't make it too hard. If you know the initial velocity and the mass, the final velocity,
oh yeah, just yeah.
then find change in P.
Okay.
Or it might tell you the initial velocity and the mass and the final velocity and the time and ask for the force.
Yeah. Okay.
And you can do that too.
Yeah, that makes sense.
Is that okay? Other things from this sheet. Clarification that you would like from anything? My goodness. Oh. Just one note that might be helpful to just keep in your brain.
Yeah.
There are two really simple equations from this like set of units. You have delta P is equal to F delta T F net times T. That's the impulse momentum theorem. There was also another really simple theorem that we had. It was the work energy theorem. That one sound familiar? Work is also equal to force times distance, where the force and the distance are parallel to one another. They both have forces in them. Okay? But paying attention to how they're related is important. One has like a certain distance that you're going, one has a certain time. You can intermingle them and mix them together, but just to be aware of what's what there is a good thing.
And if like the force was, if it was like on like a ramp, you just find the
force and the force and the displacement have to be parallel.
Yeah. Okay.
Yes. We good there?
Mm-hmm.
Simple harmonic motion and waves. So this one was like on a very light color buff sheet, maybe. What questions or what things did you want to go over on this one? There are a lot of things on this one, I know. It's kind of, sometimes it's kind of overwhelming, I feel like, but.
Yeah.
Yeah, sorry. I wasn't trying to ignore you. I just was in my own little world.
6D32.
6D32. Again, if I can find it, I will do it. 6D32 is right there. Boom. 6D32 says, the student is able to predict the properties of standing waves that are a result from the addition of incident and reflected waves that are connected, or excuse me, are confined to a region and have nodes and antinodes.
Is that about like pipes and stuff?
So it'd be about pipes and strings. Yeah. So knowing the relationship between frequency, wavelength, and velocity is what they're getting at there. Knowing that the reason that you have a standing wave is because you have one wave that's going in, reflecting off the end, and then bouncing back, inverted, so that it's going to interact with that other wave, right? Because standing waves are a result of superposition of two waves. Does that make sense? One going this way, one going this way. And only at certain frequencies will those waves constructively interfere at the same spot and destructively interfere at the same spot. Does that answer the question you're asking me? Do you want me to say more things?
I keep coming across the same problem.
Oh,
Like
okay.
this when I've been doing stuff. And then we had a test, but it's about two tubes. One is shorter than the other.
Yeah, we did that one on a test, didn't we?
You did that one on Friday?
No, we did that on a test.
Yeah.
Uh-huh.
And I keep like revisiting it, and I can't figure out exactly. Like, I know like the gist of it, but I can't figure out exactly what it is.
What the problem is or what the answer is?
Like what the answer is. Because I know like it says that when the at lower frequencies they have different.
They don't have the same deal, but then at a higher frequency, then they can resonate at the same frequency.
Yeah.
So, yeah, so we did this one on this test, but let's just talk it through. So if you have two tubes that are different lengths, that means that their fundamental frequencies are going to be different. Do you guys agree? Okay, so if we found like a fundamental frequency in this one, is it closed at one end, I think?
Yeah, one
Okay.
is closed, one is open.
So it's going to look something like this, right? Whereas that same wave is going to be like somewhere like, I don't even know, not anywhere near a standing wave for that second one, right? Does that make sense? And when you have a standing wave for the big one, something like this, well, I'm really bad at drawing the standing waves, then this one's going to be, definitely not a standing wave either. So they won't both resonate at the same frequency when they're at low harmonics or at low frequencies, okay? But when you get to higher frequencies, what happens to the wavelength? It gets shorter. So you could have like a situation, and this is not going to work out perfectly, but you get the idea. Something like this. Is that okay? Whereas in this one, if it looks the same, so I'm going to try and line this up nicely. Oops, I missed, but you get the... They can both have a resonating frequency with the same wavelength, which means the same frequency. It's just a different number. It's a different harmonic number. Does that make sense, Will?
Yeah, perfect. Thank you.
Yeah.
What was the equation for finding the harmonic again?
Well, it depends on if you have a closed. Closed is different from open.
Okay.
So open and string is the same, and it's F is equal to V over 2L times N.
So the string and an open one have the same.
Yeah. Because on a tube that's open at both ends, you're going to have antinodes at both ends. A string's going to have a node at both ends, so it's the same situation. Go back and look at your notes.
Okay.
I can talk you through it some more if you need to.
Yeah,
And
okay.
this one's going to be V over 4L
Okay.
times N, but N has to be odd
Okay.
for a closed. What else? Are there other things from this set of learning objectives that I can solidify for you, answer for you? I'm doing okay? Okay. So,